Well, it was 20 years ago, June the 1st, 1984, maybe 19 years ago. Steve Wolfram was 25 years old. He got onto an airplane in New York City to fly to London. The plane took off. Somewhere over the Atlantic, Steve pulls out a sheaf of papers, and if you were sitting next to him on that flight, you would have thought, well, this is not a particularly normal person, because the papers were a printout from his computer, and they looked kind of like a crossword puzzle. There was rows and rows and rows and rows of boxes. Some of them were black, some of them were white. There was one black box on the top line, and then if you went down each row, there would be more black boxes here, and black boxes there, and white boxes here, white boxes there, and as you kept turning the pages, they would form patterns, and then the patterns would go away. So imagine sitting next to a guy in a plane who's staring intently at black boxes and white boxes and turning the page, and when it gets really weird is as you look on down in this pattern, the patterns disappear. And the crossword puzzle kind of goes berserk, and you get this crazy quilt, patternless, chaotic jumble of black and white boxes. And so now you got this guy staring at pretty much just nothing, like a mess, a riot, chaos on a page. And the odd thing is, he seems to be loving it. I mean, he's over the moon with excitement. It's like he's been hit with a thunderbolt. And he later tells the London Daily Telegraph that that printout, and we will hope to show you it tonight, is the most important thing I've ever seen in science. He just had a profound insight in his intellectual life, or so far anyway. It led to this enormous book where it says on the very first page, what I had seen was the beginning of a crack in the very foundations of existing science and the first clue to a whole new kind of science, which is, of course, the title of the book, A New Kind of Science. So tonight we're going to figure out, or try to figure out, what it was that Stephen saw, so you can decide if what made him gasp will make you gasp. Let's welcome Stephen Wolfram.
Here's the image that Wolfram was studying on his flight to London. It's a visual readout of a computer program known as a cellular automaton. These programs are simple rules that determine sequential patterns of black and white squares. Starting with a single black square in step 1, a computer can run any number of steps afterwards, revealing the structural pattern that each rule will produce. Some of these patterns are very simple or have a basic repeating structure to them. But other rules, like rule number 30 that Wolfram was studying on his flight, seem to produce structures with endless complexity and no obvious repetition. The pattern of rule 30 is so complex, in fact, that nearly 40 years after he discovered it, Wolfram is still working on it. For example, in 2019, he offered prize money for anyone who could answer 3 specific questions about the structure of rule 30. But cellular automata are just one aspect of Wolfram's computational expertise. Since the 1980s, he's made every effort to communicate his findings to the general public, starting with his software platform Mathematica. In 2002, Wolfram published his 1,200-page book, A New Kind of Science. NKS, for short, was Wolfram's boldest attempt to explain the meaning of the computational universe, not only for scholars and specialists, but for anyone curious about theoretical science and how to understand the universe. This is where he discussed cellular automata in detail, leading to a new computational principle of nature. NKS is Wolfram's magnum opus, and it challenges us to revise some of our most basic intuitions about modern science. To reveal the deeper meaning of this work, we need to understand Wolfram's intuition about why this is so important. So let us investigate the true value of Wolfram's scientific genius. When it comes to science, Wolfram was a true child prodigy. His first scientific paper was published in 1975 at 15 years of age. At 20, he earned a PhD in particle physics and became a professor at Caltech in 1981. This was the year that Wolfram received the MacArthur Genius Award, which was an important moment in his life because it initiated him into the tradition of modern science. One of the key figures in Wolfram's life at this time was the physicist Richard Feynman, who also served on Wolfram's PhD council. In his letter to the MacArthur Foundation recommending Wolfram for the award, Feynman wrote, "He has made himself fully aware of all the problems in fundamental theoretical physics, from gravitation, cosmology, and the new unified field theories, to the detailed problems of hadron physics and the weak interactions. The method he uses in studying each question is not so much to read about it, but to work it all out himself. Such methods and such industry is, of course, the true source of creativity and originality. I don't know of any others in this field that have the wide range of understanding of Dr. Wolfram. He seems to have worked on everything, and has some original or careful judgment on any topic." In the following years, Wolfram began to focus on wider problems of theoretical science, or what was known as complexity research. But by the fall of 1985, he was becoming frustrated with academia, and wrote to his mentor for advice. "I am being treated increasingly badly at the Institute for Advanced Studies, and really have to move. I can't see anywhere that would really be nice to go to, and would support the kinds of things I am now interested in. So I'm thinking of trying to create my own environment by starting some kind of institute. It would be so much nicer if such a thing already existed, but it doesn't. You probably think that doing something administrative like this is an awful waste of time, and I am not sure that I can disagree, but I feel that I have little choice, and given that I am going to do it, I would like to do it as well as possible." Feynman wrote back to Wolfram a few weeks later, "It is not my opinion that the present organizational structure of science inhibits complexity research. I do not believe such an institution is necessary. You say you want to create your own environment, but you will not be working in this environment, you will be administering it. And the administration environment is not what you seek, is it? You won't enjoy administrating people because you won't succeed in it. You don't understand ordinary people. To you they are stupid fools, so you will not tolerate them or treat their foibles with tolerance or patience, but will drive yourself wild, or they will drive you wild, trying to deal with them in an effective way. Find a way to do your research with as little contact with non-technical people as possible. With one exception, fall madly in love. That is my advice, my friend." Feynman was wrong about Wolfram's ability to be an effective administrator. He seems to have done a great job as CEO of his own company, and personally engages with his staff and followers on social media. In the approximately 40 years since he left academia, Wolfram has built his reputation as a public intellectual, serving as a guest speaker for different conferences and events, and appearing on various talk show podcasts. He was even invited to Washington in 2017 to give his testimony on how artificial intelligence should be integrated with social media. His advice is really quite interesting, and I recommend checking out the clip on his YouTube channel. Wolfram is at his best when he's discussing the computational universe, really allowing his true enthusiasm to shine. His most recent enterprise, known simply as the Physics Project, is an effort to reconnect the computational universe with fundamental physics. By inquiring into the very notions of time and space, the Physics Project is on the verge of becoming a theory of everything. This ambition has drawn interest from a whole new generation of scholars, and is an exciting time for Wolfram and his team. The Physics Project basically continues on from where a new kind of science left off, specifically from Chapter 9 on fundamental physics. I'll be taking a closer look at this particular chapter later in the video, but first I want to consider NKS as a whole. The book is about 1,200 pages long, split between 846 pages of text and images, with 351 pages of notes at the back. NKS is an incredibly visual work, with impressively detailed figures and tables. Many of these are derived from cellular automata like Rule 30, but add extra layers of complexity and variation. The entirety of NKS can be found online, but I've always enjoyed sifting through the pages and stumbling upon a new image or graph that I'd missed in the past. It should be mentioned that Wolfram is an excellent communicator, and NKS is an enjoyable read. The images have succinct descriptions, and the paragraphs are clear and concise. So there's really no problem understanding what Wolfram is saying. It's harder to understand why he's saying it. And to this end, we should take advice from Erwin Schrödinger. The task is not so much to see what no one has yet seen, but to think what nobody has yet thought about that which everybody sees. So what this means is that this would be a more accurate title for the book. It's not the cellular automata that are really interesting, it's Wolfram's thoughts about them. And to his credit, Wolfram recognized the central role of intuition in his project. He dedicated a subsection of Chapter 3 to this very idea. We know that computers can perform many complex tasks. In a system like a cellular automaton, the underlying rules can be thought of as rough analogs of the machine instructions for a computer, by any measure simple to describe. Yet when we ran them, we ended with patterns so complex that they seemed to defy any simple description at all. The whole phenomenon is something much larger and stronger. In a sense, the most puzzling aspect of it is that it seems to involve getting something from nothing. One might hope that it would be possible to call on some existing kind of intuition to understand such a fundamental phenomenon. But in fact, there seems to be no branch of everyday experience that provides what is needed. And so we have no choice but to try to develop a whole new kind of intuition. It's possible that Wolfram underestimated the magnitude of the social shift required for this intuition to be created. It's important to interpret his claims through this lens, because otherwise he sounds just obsessed with his own personal revelation.
Hi. I was wondering if you had any thoughts or feelings about Wolfram's new science?
Yes. Splendid book. I love the book. I think it's wonderful. That said, has Stephen Wolfram reinvented science? He has in his own head.
The thing about Wolfram is that he's remained convinced even in the face of ridicule. This echoes and maybe inverts Feynman's remark about Wolfram seeing ordinary people as stupid fools. It's simply the case, though, that Wolfram makes dubious claims with a resolute conviction. It's as if he's ahead of his time, and we just can't appreciate the computational universe like he can. Listen to how he responds to Robert Krulwich in this interview after the publication of NKS.
Why do a book? I mean, why not, if you had something in your mind, why not do what Albert Einstein did and just, publish whatever it was you wanted to say in scholarly journals, assessed by referees, read by scholars? Why did you choose to do it this other way?
Relativity is a simpler concept to explain in 10 pages than what I'm trying to talk about.
That's your answer?
Well, that's part of the answer.
Yours is a bigger revolution. You have a bigger revolution in your head, or something just more complex to describe?
It's a bigger intellectual framework.
It's just that I don't think you could build a Sistine Chapel out of this kind of thing, but that's just maybe a prejudice.
Well, if I'm right, it was built that way.
Okay. We should talk about modesty for a second here. In the book, you describe this theory as one of the more important single discoveries in the whole history of theoretical science. You also say in your preface, I've discovered vastly more than I ever thought possible, and in fact, what I've done now touches almost every existing area of science and quite a bit besides. Is it...
I wouldn't have read it with quite that intonation.
Well, I'm goofing on you, but the question, I guess, is there is normally in scientists a adamant modesty. I mean, they're like always so scared to declare something's true, because if anybody in the universe finds out it isn't quite true, then they're wrong. So it's always so tentative. You, however, seem to break the pattern.
Depends on what scientists you talk to. I think
There are two main ideas that can help us to understand Wolfram's intuition. The first is the production of complex phenomena from simple rules. This is basically what happens with cellular automata, but is ultimately a more general principle of how to understand nature. The second is the categorization of the theoretical sciences, including physics, mathematics, and computation. This helps to situate Wolfram's accomplishments within the wider scientific tradition. Wolfram presents both of these ideas in his own words during a 2003 interview with Charlie Rosen.
So one of the big questions is sort of, if you have a very simple program, what might it do?
Right.
You might think if the program is really simple, it's always going to do something very simple. Here's an example of how this works. This is a program, it's called a Cellular Automaton.
Right.
And you have a line of cells that are either black or white.
Right.
And then in successive steps, it just evolves down the page.
Right.
There's a very simple rule here that says what color a particular cell should be based on the color of cells on the step before.
Right.
You start off with one black cell. In this case, you get just a very simple, uniform black
Right.
pattern. Okay, so it was a simple program. You started it from something simple. It made something simple.
Right.
This is kind of what we would intuitively expect. This is
Right.
what I would have expected before I started doing the computer experiments I did.
Right.
So then the question is that always how it works, or can other things happen? So this is another example. Here's just another one of these programs. We started off from one black cell up here, and then we let it run for a while, and this is what we get. This is something much more complicated.
Yeah.
Still, you can see some regularity. This
Right.
ends up being one of these so-called fractal or nested patterns in the end. But this is, again, something which, where we can already see that even though the rule is very simple, the pattern we get is slightly more complicated.
Okay.
Okay, the thing that was really sort of the thing that really made me realize that there was something more going on that I didn't understand was something that I first saw in the middle of 1984. And it's this picture. This is a thing that in the scheme for specifying these programs is called Rule 30. And the way this works, this is the rule, this is the whole program up here.
Right.
You started off from one black square here,
Right.
and then this is what you get. And what's remarkable about this is, even though it looks like you sort of didn't put anything in, you just have a very simple program,
Right.
you put in one black cell, you get out this complicated thing here.
Right.
And this is something, this sort of violates our normal intuition, because normally when we think about sort of building things in everyday life, in engineering and so on, if we want to make something complicated, we expect that we need to go to a lot of effort to make that complicated thing. But this is a case where that's not happening. We have a simple rule, we have a simple initial condition, and yet we get something complicated. And it seems sort of, it effortlessly produces something complicated. What's, I think, particularly interesting about this is when we look in nature, we also see lots of complicated stuff that's been made seemingly effortlessly by nature. And so the thing that kind of really got me excited about this was the idea that perhaps whatever is going on here is also the essence of what's going on in nature and the way that nature makes complicated stuff.
Fair to say you were looking for a big idea, or that these tools would lead you to a big idea?
At the time, I wasn't sure how big the idea would be.
Okay.
At the time, all I knew was there's something missing, there's something, I'm getting blocked somehow.
Fair to say that it was mathematical equations were not taking you where you wanted to go?
Yes, mathematical equations are sort of the proudest achievement of the traditional approach to theoretical science. And they've been sort of the mainstay of what's been done in the exact sciences for 300 or so years. And I believed, as most people have, that this would be the way to make progress on things.
So you went out to do your garden, and you didn't have a rake or a hoe, and you needed to find one to figure out what was in your garden.
Yes, so I got interested in what could one do if one wanted to go sort of beyond mathematical equations, and what else might there be out there. And one kind of realizes if one wants to do theoretical science, one has to believe that the universe, that nature follows some kind of definite rules. The issue is, what are those rules made from? Are those made from the kind of constructs that people have put into mathematics, or might there be something more general, something beyond mathematics that the universe might be using to figure out what it's going to do? And so what I started realizing was there are more general things than what's in mathematics and calculus and numbers and equations and these sorts of things. And what one realizes is that computer programs, the kinds of things that we put into computer programs, give us a sort of concrete way to think about more general kinds of rules. So what I got interested in the early 1980s was sort of what else is out there if one looks at more general kinds of rules than the ones that have been used in mathematics. What is there that the universe might be using?
Wolfram's intuition of a science beyond mathematics is an essential clue to unlocking his vision of the computational universe. It's not inherently mathematical, but can still teach us about the natural world. Along with physics and mathematics, computation is a theoretical science that has its own distinct subject matter. So to begin our evaluation of Wolfram in earnest, we must revisit the origins of theoretical science in ancient Greece. According to Aristotle, there are three categories of theoretical science. The first is physics, which studies things that are separable and movable. Then mathematics studies the inseparable and immovable, and finally theology, the separable and immovable. Theology is the most general of the three, which Aristotle also refers to as first philosophy, or the science of being qua being. Theology studies things that are not inherently mathematical, nor do they have any qualities of physical objects like size, shape, or color. They actually don't have any properties at all, except for their being as such. In other words, the science of being qua being is the study of the most general theoretical constructs that we can actually have knowledge of. Aristotle defines this as theology, since it is obvious that if the divine is present anywhere, it is present in things of this sort. Now, I wouldn't say that Wolfram has gone as far as Aristotle in attributing theological meaning to computation, but this still demonstrates the potential scope of his intuition about a subject matter that's beyond mathematics. Wolfram has clearly been thinking about this in the meantime, for example in this blog post from May 2021. The history of physics might make one think that numbers would be a necessary part of the structure of any fundamental theory of our physical universe. But the models of physics suggested by our physics project have no intrinsic reference to numbers. Instead, they just involve a giant network of elements that's continually getting rewritten according to certain rules. There aren't intrinsically coordinates or quantities or anything that would normally be associated with numbers. And even though the underlying rules may be simple, the detailed overall behavior of the system is highly complex and full of computational irreducibility. But the key point is that as observers with particular characteristics embedded in this system, we're only sampling certain features of it. And the features we sample, in effect, tap into pockets of reducibility, which is where simplifying concepts like numbers can enter. The origin of the way we sample the universe has deep roots in the nature of our consciousness, and our fundamental way of experiencing the universe with our particular sensory apparatus, place in the universe, etc. The idea that numbers are simplifying concepts that allow us to sample the universe goes back before Plato and Aristotle to Pythagoras. The Pythagoreans saw numbers as the very substance of the cosmos, and there was no meaningful distinction for them between a physical thing and its countableness. Numbers were studied as one would study light or sound, having an experiential quality attached to them rather than serving as tools for counting and measuring. The Pythagoreans were known as a kind of religious cult and accrued their own mythology through the ages. They worshipped a symbol of numerical perfection known as the Tetractys. Their oath read, "I swear by the discoverer of the Tetractys, which is the spring of all our wisdom, the perennial fount and root of nature." The Tetractys functioned as a simple fourfold rule that explained the behavior of complex systems in nature. This included mathematical objects, such as the point, line, surface, and solid, as well as the consonant intervals of harmony, namely the octave, the fourth, and the fifth. Beyond this, the Tetractys also explained how human society was structured according to individuals, families, villages, and cities, while a human life progressed through childhood, adolescence, maturity, and old age. In computational terms, we might say that the Tetractys is what the Pythagoreans used to sample nature, or simplify the universe according to a deeply rooted structure of consciousness. So how does the Tetractys fit into the computational universe? Well, in Chapter 3 of NKS, Wolfram describes a special type of cellular automaton called the Mobile Automaton. This is still a rule-based program, but it contains a single active cell, meaning that the sequence is updated based on this one cell and its immediate neighbors, instead of all of the cells being updated in parallel. In Chapter 9 of NKS, Wolfram uses the Mobile Automaton sequence as a model for spacetime. It functions like a causal network, having a single observation point embedded within the active cell. Here are the ways in which Wolfram visualizes this model of spacetime in its most general form. Figures F and G on the bottom clearly resemble the triangular array of the Tetractys. The key difference being that they have connections between the nodes, which have a fixed direction starting from node 1 and progressing through the arithmetical sequence. Wolfram claims that this directional aspect of the model corresponds to our human perception of time as sequential and non-reversible. To find the tetractys in figure G, for example, simply remove the numbers on the nodes and the connections between them. But of course, this strips Wolfram's model of its unique computational character. So perhaps the tetractys is like a primitive form of the mobile automaton, and Wolfram's model actually represents some scientific progress in our understanding of these pure elements. However, he was not the first to have done so. One of his major predecessors in this regard was the 17th century philosopher Robert Fludd. Fludd studied at Oxford and was a physician by trade. He traveled Europe as a young man, and by 1617 was publishing massive illustrated tomes about all sorts of topics. He divided the universe into the outer macrocosmos and the inner microcosmos. This comprises what I call Fludd's cosmological system. I had the chance to study some of Fludd's original manuscripts in Amsterdam, and took this photo here of a special little tetractys that I found. The tetractys makes many appearances in Fludd's books. He frequently modifies it with numbers, letters, and dotted lines. He also expanded it from a fourfold to an eightfold pattern, like in this figure here, which more closely resembles Wolfram's mobile automaton. This shows that Fludd was also considering how we can sample the pure elements of this simple rule. Here are 3 more examples from Fludd's writings that show some of his other approaches. One feature that these diagrams share is a dividing line between the typical fourfold pattern and the expansion to the eightfold, separating lines 1 to 4 from lines 5 to 8. Fludd also tended to reflect the eightfold back on itself, resolving it into the unity of the initial tetractys. Of the many versions that I've been able to find, this one here seems to be the most intuitive. I say this because it illustrates Wolfram's intuition about the categories of theoretical science according to Aristotle's metaphysics. First, we have objects of physics. These are subjected to the forces of generation and corruption, like the natural phenomena that require us to sample them. Fludd's sampling method here uses the numbers 1 to 4. Secondly, there are the objects of mathematics, which are distinct from those of physics, yet not clearly separable from them. They're not subjected to the forces of change, and thus do not require any sampling. In fact, maybe the tetractys permits the sampling of physical objects in the first place. Finally, we have theology, which takes into consideration no particular qualities of math or physics, and just views the entire sequence as nothing but pure elements. Theology makes no explicit reference to sampling, yet is entirely separable from the specific objects that it represents. This indicates that theology, according to Aristotle, is the most generalized and the most simplified form of science at our disposal. As part of the physics project, Wolfram has recently been developing a concept he calls the Ruliad, which is the limit of everything that is computationally possible. Listen to how he describes it, and see if you think it sounds similar to the eightfold pattern in Fludd's system.
One of the consequences of this view is that, in some sense, physics and mathematics are built on the same thing. They're both built on the Ruliad, and they are, in a sense, they are the same thing in some sense. They are simply being observed in different ways. You get physics, you get mathematics. Another consequence that has is, remember, I was talking about Euclid having this view that mathematics is something which is a crispening up of common human experience. Well, now we've got a picture where, in a sense, mathematics is an extraction from the Ruliad made by human experience, just as physics is an extraction from the Ruliad made by human experience. And the question is, and that then gives one the idea that mathematics has a reality to it, just like physics has a reality to it, that is something extracted by our human experience.
It's good to see that Wolfram is starting to focus more on human observation and what his theory of computation tells us about being human. It's too easy to assume that computation is just a mechanical or inorganic theory that only applies to technological problems. There is an existential side to computation, which Wolfram describes in the final chapter of NKS on the principle of computational equivalence. Among principles in science, the principle of computational equivalence is almost unprecedentedly broad, for it applies to essentially any process of any kind, either natural or artificial. And its implications are both broad and deep, addressing a host of long-standing issues, not only in science but also in mathematics, philosophy, and elsewhere. The key unifying idea that has allowed me to formulate the principle of computational equivalence is a simple but immensely powerful one, that all processes, whether they are produced by human effort or occur spontaneously in nature, can be viewed as computations. It is perhaps a little humbling to discover that we as humans are in effect computationally no more capable than cellular automata, with very simple rules. But the principle of computational equivalence also implies that the same is ultimately true of our whole universe. So while science has often made it seem that we as humans are somehow insignificant compared to the universe, the principle of computational equivalence now shows that in a certain sense we are at the same level as it is. For the principle implies that what goes on inside us can ultimately achieve just the same level of computational sophistication as our whole universe. Seeing human beings as reflections of the entire universe is an ancient idea that Flood was trying to communicate in his pictures, not only from his own point of view, but taking into account the philosophical and spiritual traditions that have contributed to our collective understanding of the idea. It's not surprising, then, that we can view many of his diagrams through the lens of computational equivalence. For example, this image on the left is a macrocosmic structure, while the image on the right is a microcosmic or human structure. The 4 concentric circles that define the template of each image are like a geometric or spatial version of the eightfold pattern we examined earlier. The circles divide the universe and man into discrete regions, like the sampling of physical objects. Flood uses symbols to indicate specific qualities or points of interest in these structures. One of the main symbols is the central sun, located at the midpoint or sphere of equality. Here's a closer look at the relationship between inner and outer complexity. One curious feature of the image on the left is that it exhibits a nested pattern surrounding the sphere of equality. So perhaps the central sun functions like the active cell of a mobile automaton, and for human beings this would occur at the spiritual heart center. Flood's works are an illustrated exhibition of what the principle of computational equivalence implies. And recalling Wolfram's intuition about simplicity, these diagrams can also produce a degree of intellectual complexity that's not immediately apparent on first glance. Perhaps Flood's system demonstrates with full sincerity the divine implications of theoretical science, at least according to Aristotle's definition. I will be talking more about Flood in other videos, but will mention here that he was criticized by scientists like Kepler in much the same way that Wolfram was, namely that Flood had only explained the cosmos as it appeared in his own mind. He was also criticized for using mathematical units incorrectly, although he was clearly aspiring to a level of thinking that was beyond mathematics. In retrospect, we can appreciate how the intellectual lives of people like Kepler and Newton had an amusing mixture of fact and fantasy. But skepticism has been around for a long time and encourages us to seek out logical inconsistencies and appeals to subjective experience. The latter is particularly troublesome for thinkers like Wolfram, who aspire to the most general possible level of theoretical science, for when this level is achieved, it will inevitably produce results that apply in equal measure to both subjective and objective phenomena. An extrapolation of the principle of computational equivalence might state that the most general concepts must necessarily apply to all possible configurations of human knowledge. We are literally the universe becoming aware of itself, yet still cling to the absurd belief in our capacity for detached observation. We really have no choice but to assume that underneath all multiplicity lies an indivisible unity, and we can infer this unity from the harmonic relationships between quantities and qualities. Of course, this is not our common intuition about the world, even when we're doing science in the modern sense. We still follow the analytical method of Aristotle. But Wolfram represents a kind of return to the earlier vision of unity described by Pythagoras. Hence, Wolfram confidently states how major philosophical dilemmas, like determinism versus free will, are resolved through this computational universe approach. At the very least, his confidence should inspire us to seek out unity for ourselves, and ultimately to remain optimistic about the future of science.
If my shoe's a computation and I'm a computation and this glass is a computation, you know, if we're all kind of complex, the shoe, the glass, and me, then any one of us could think. It just happens to be odd that I'm thinking, or I think I'm thinking. But,
Right.
But in your lights, everything could think.
Right. Well, so one of the questions is there sort of an abstract distinction between the kind of computation that happens in the case of, for example, human intelligence and the kind of computation that happens in, let's say, a turbulent fluid?
Right.
And I certainly would have had the intuition before I looked at the things that I looked at that there would be some sort of fundamental difference. What I've now concluded from the things that I've looked at is that there really isn't, that it's really, there's a sort of fundamental equivalence, at least at the level of sort of the sophistication of computations that can happen between what happens in, let's say, a turbulent fluid flow and what can happen in something like a brain. And that's in a sense...
So doesn't that bother you if I say this equals your brain? Seems like someone's suffering in the comparison.
Well, so one of the things is that this whole phenomenon of kind of when we look at something like that complicated cellular automaton, that Rule 30 cellular automaton thing, when we look at this, we can ask the question, why does this look complex to us? Right. What's the sort of fundamental reason? Well, I think it has to do with this comparison between our brains and things like splashes of water and things like the Rule 30 cellular automaton. Because what we're kind of used to, I mean, science, one of the kind of basic idealizations in traditional science tends to be the observer is kind of infinitely computationally powerful relative to the systems that they're observing. I mean, it's been one of the trends in science that we've gotten more and more realistic about what we as observers can actually do. That was sort of a fundamental thing in relativity and quantum theory, right, and other kinds of things. Well, what happens here is that one's getting sort of realistic about the computational abilities of the observer. If the observer is sort of infinitely computationally powerful relative to something like one of these simple abstract cellular automata, then the observer can decode what it's doing. Then it may be going and sort of updating every cell in some way that it thinks is very elaborate, but we, as kind of infinitely computationally powerful things, can always decode what it was doing, right, and can say, well, even though it may have taken you 1,000,000 steps to do this, I can work out immediately what will have happened after 1,000,000 steps. Right. What I'm saying here is that in fact that isn't really right, that we're not really infinitely computationally powerful relative to systems like this. In fact, we're computationally equivalent to systems like this. So that means that the computations that we can do to predict these systems are no more sophisticated than the computations that these systems in effect do themselves to work out what they're going to do.
Well, in plain English, that means that if I'm really trying to figure out how a cloud works or how cornflakes pour out of a cornflake box, that may be too complicated for me to get, and I may not ever be able to predict.
Well, so
wait a second, doesn't that mean that you've taken science, which has always had as its greatest power, the power to predict? If I shoot the cannonball up in the air, thump, 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 I know where it's going to land. But in your science, because everything is, or many things are very complicated, equally complicated, nobody can figure out what anybody's doing because everybody's equally mystified. That seems a little weak for science.
Well, it isn't. In a sense, so it kind of goes in two directions. One thing is, it's pretty useful to know what the sort of ultimate limitations of one's methodology or one's science are going to be. It would be unfortunate if we kind of went along thinking we'll be able to write down a mathematical equation for everything, which is kind of an idea that one might have had from sort of early progress of physics and things like that. If in fact there's some fundamental obstruction, there's some fundamental reason why one can never do that, it's useful to know that. And in fact, one can make predictions even from just knowing that one can't write down a formula. One can make predictions about how this or that thing must seem random because there can't be a formula that can be written down for it, things like that. But what happens is that what you see is that there's a certain sort of ultimate computational irreducibility to phenomena. There's sort of an ultimate point beyond which you can't compress what's going to happen, beyond which you can't make predictions about what will happen sort of faster than the system itself does its thing. But in a sense, there's an awful lot of science that can be done in these kind of pockets of reducibility that, for various theoretical reasons...
But there's an awful lot of science that probably can't be done because we're not able to compute faster than even a rock, maybe, if there's a really smart rock around.
Well, and that has things to say about all sorts of questions, like, for example, questions about determinism versus free will, for instance. Right. There's sort of a mystery about, if we follow definite rules, why is it that we seem to be acting in a way that's free of definite rules and a way that's very hard to predict? Well, this phenomenon of computational irreducibility gives us kind of a scientific basis for that kind of everyday phenomenon that we observe.
I mean, a computer is running through me, and all my actions are determined by the simple rule in the machine from the other universe, or wherever it is. But I can't know it because it's so complicated, I can't read it, so I'm both predetermined and I have no idea what the future is because I can't read it. Well, I should read some questions because other people want to get out of here probably pretty soon. So here are some questions.